Suppose we have two samples of numerical data, two lists of numbers from two different samples. The data do not come in matched pairs, and I want to know if there's a difference here, if there's a statistically significant difference between these things. Suppose I do an experiment. I grow a bunch of tomato plants. Some of the tomato plants are randomly selected to receive fertilizer, and some of them are randomly selected to not to. My control group, I measure the weight of the tomatoes produced by each plant, and I record that, and then I want to see, is there a statistically significant difference here? I have data on the scores of students from two different high schools on the SAT test, and I want to know, well, the averages look different, but is it a statistically significant difference? And if so, how much? I want to look at that. How about this? I'm studying cancer treatments. I have a group of cancer patients. I administer two different treatments to two groups of them and measure the average change in tumor size from those. And I want to know which of these two treatments is more effective at reducing tumor size. These are all examples of cases where I want to compare the difference in the averages of two different samples of numerical data. Here's an example of a study which is of particular relevance to me. As the parent of some young kids, I'm rather interested in what can I do to help my kids actually eat something at mealtime and not always be snacking between meals. So this is a really cool study that was done. It involved 47 kids and their parents. The kids were aged 6 to 10 years old. And what they did is they randomly separated it into two groups. In the experimental group, there were 25 kids who worked with their parent and helped prepare a lunch of pasta, breaded chicken, cauliflower, and salad. In the control group, the kids just played or read a comic book or something like that while the parent prepared the same meal, and then they sat down and they ate, and they measured the number of calories consumed by the kids in order to see if anything made any kind of a difference at all. This was, note, a controlled experiment. They randomly divided their sample into two groups. They treated the two groups differently and then measured the result of that. And so this really is a true controlled experiment. And if you have a controlled experiment, then there's at least a potential for establishing a cause-effect relationship here. This study, if it works, could establish that helping to prepare a meal causes children to consume more calories on average. So what's the first thing we do? Well, before we go into our hypothesis tests and our confidence interval, we got to play with the data. We got to examine the data. In this data set, treatment 1 is the group of kids who helped prepare the meal. Treatment 2 is the control group. Here are all my various R commands. So I read in the data, then I subset it. I said, okay, let's put treatment 1 into data frame kid 1, treatment 2 into data frame kid 2. One of my favorite things to do that works very nicely for this data set is to do a side-by-side box plot. Notice here I run the box plot command, and then I put in the one data set and the other data set. And, you know, this is kind of nice. It's a nice way to see what's going on. It looks like from the box plot, that looks pretty good. The kids who are in group 1 who helped prepare the meal looks like pretty consistently. I mean, there's some overlap here, but it looks like that might be a statistically significant difference. We can see the means are larger, the standard deviations, the 5-number summaries are pretty consistent, but it looks like if the kids are involved in that, it looks like they're doing better. Okay, good. Now we've got a sense of where the data is. No weird outliers, nothing terribly strange going on here. This looks kind of interesting. Histograms show that they're not too far away from a mound shape, from a bell curve shape sort of thing. So we're probably justified in using the t-distribution to analyze this data. All right, it looks like we have a difference here. Let's conduct a formal hypothesis test to see if we really have one. What's the null hypothesis? Well, the null hypothesis is nothing to see here. It's all just due to random chance. Don't worry your pretty little head about it. In this case, the null hypothesis says it doesn't make any difference. Whether or not kids help with meal preparation has no effect on the mean number of calories consumed one way or the other. So we would write that as null hypothesis is mu1 equals mu2. The population 1 average is equal to the population 2 average. The alternative hypothesis says no, this involving kids in meal preparation has an effect on the average number of calories consumed. In this case, we're going to do a two-sided alternative hypothesis. I would be interested, it would be meaningful to us either way. If the kids who played or read comic books while mom or dad makes the meal, if those kids consumed more calories, if they ate more of their meal, you know what? That would be interesting. I would want to know that. And so as a result, either way, I want to know about that. So the alternative hypothesis is just that mu1 doesn't equal mu2. Choose a significance level of alpha 0.05. All right, here's the big new thing. For this, since we have two different samples, each with their own means and each with their own standard deviations and each with their own sample sizes, the way we compute the standard error is new. It's going to be a big giant square root. And what's the square root of? It's the first sample standard deviation squared divided by the first sample size plus the second sample standard deviation squared divided by the second sample size, and then the square root of that whole thing. So in this case, we have the square root of 105.7 squared over 25 plus 99.5 squared over 22 and the square root of the whole thing. So that gives us a standard error of 29.9. That's how much we would expect the difference between the two sample means to vary from sample to sample. If we did this many, many, many times, each time getting two different samples and then finding the difference between x bar 1 and x bar 2, I would expect that all those different x bar differences would have a standard error, standard deviation of about 30 calories in this case. All right, we need our test statistic, a t-test statistic, because this is based on sample standard deviations. In this case, I want to compare the difference I got, the difference between my two sample means, with what the null hypothesis says. Well, in this case, the null hypothesis says there should be no difference at all. So mu1 minus mu2 would be just 0. And my numerator is just x bar 1 minus x bar 2. So that's 431.4 calories minus 346.8 calories, all divided by 29.9. And that's a test statistic of 2.83 standard deviations. That looks like that might be statistically significant. That's more than a couple. What do we do for degrees of freedom? We have two different sample sizes, one sample of 25, one sample of 22. In order to be cautious, we take the smaller sample size and then we subtract 1 from that to get our degrees of freedom. So in this case, degrees of freedom is 22 minus 1 equals 21. So for our p-value, again, this is a two-sided test because that alternative hypothesis just says mu1 doesn't equal mu2. So we have 2 times quantity 1 minus pt of 2.83, 21 degrees of freedom. Close the quantity, and that's a p-value of only 1%, 0.01. All right, so we have something interesting here. This is a statistically significant difference. This is less than alpha. That's less than 5%. This would be really unlikely to happen. That's only a 1% chance. That would only happen 1 time in 100. Would you get something as interesting as this? You would get 2 sample means as different as this if the null hypothesis were true and there's really no difference at all. So as a result, the null hypothesis probably isn't true. So we reject the null hypothesis and we say yes. Whether kids help with meal preparation does cause them, if they help with meal preparation, that will cause them to eat a larger mean number of calories. All right, so how much more calories? The hypothesis tells us there is a difference. Now I want to quantify, well, how much of a difference is there? In this case, we take the difference we got, x bar 1 minus x bar 2, and then we add and subtract our margin of error to this, where our margin of error, again, is our critical t-value times our standard error. And this is the new standard error, the square root of the whole big thing like we did on the last slide. So critical value is, we do QT of 0.975. We want a 95% in the interval, 5% out, 2.5% in each tail. So we have 21 degrees of freedom and we get 2.08. Okay, so there's our critical t-value. Margin of error is therefore the 2.08 times the 29.9 standard error that we found on the previous thingy. We multiply that out and we have a margin of error of 62.2 calories. That's kind of a lot. That's kind of a big deal. If I take my x bar 1 minus x bar 2 to get, okay, so what's the mean difference I got? That's a difference of 84 calories, 84.6 calories, and then I add and subtract 62.2 from it. That's a pretty wide confidence interval. Look at that. If that goes all the way from 22.4 calories to 146.8, that's a very, very broad confidence interval. That's kind of interesting. We're going to have to think about this. So what does that mean? All right, it's important to be able to compute a confidence interval. It's even more important to be able to interpret the meaning of a confidence interval. In this case, we are 95% confident that the difference between the means of these two populations is in this range. Okay, so that's a general statement. In this particular context, the two populations are the population of where we've got the kid preparing the meal with the parent and the kid playing while the parent prepares the meal. So we can say we are 95% confident that involving kids in the preparation of this particular meal will cause them to consume between 22.4 and 146.8 more calories, and this is on average. So let's consider this issue of statistical significance versus practical significance. This is statistically significant, the difference between the two groups. Yeah, that's statistically significant, meaning it's very unlikely that we would get a difference that big just due to random chance if there really was no underlying difference. But how big is the difference? That's kind of broad. So let's think about this a little bit. The mean calories consumed by kids who did not participate in meal preparation was 346.8. So what sort of a percent increaser is going on here? 22.4 divided by 346.8 times 100 to make it a percent. Okay, so on the low side of the confidence interval, that's only a 6.4% increase. On the other hand, on the high side of the confidence interval, 146.8 divided by 346.8 times 100% is 42.3% increase. Well, that's substantial. So how do we interpret this? 6.4% is pretty trivial. I mean, seriously, as a parent, the time and the effort and the energy and the cleaning up that you got to do if you involve the kids in making a meal, that's a significant investment. I'm not sure it's worth it to just get them get them to eat 6.4% more. On the other hand, if they're going to eat 43% more, well, maybe I'm willing to do that. Of course, the center of our interval is right in the middle of that. That's going to be, what, 20-something percent. So, this study clearly establishes a statistically significant difference. It clearly establishes a cause-effect relationship. However, this is what we call the effect size, and the size of the effect is all over the map. 43% is big, 6.4%, not so much, kind of trivial. So the real limitation here is the sample size. I mean, the total number of kids involved in this study is pretty small. If they'd had more kids, if that had been a couple of hundred kids instead of a few dozen kids, if that had been a couple of hundred kids, then not only would they have been able to establish that, yes, it makes a difference, but they would have been able to kind of pin down on much better, more accurately, how much of a difference this really makes. So that would be a criticism I would make of this study. Its study is good enough to know that this makes a difference, but whether the difference is trivial or whether the difference is a big deal, they can't really say one way or another. All right, so quick summary. We have analyzed two samples of numerical data, and this is the one where the data does not come in correlated pairs. I just got two lists of numbers from my two samples. Before we do hypothesis tests or confidence intervals, always look at the data, examine it, get your summary statistics, make some histograms, make some box plots, get a sense of what's going on there. Then from this, we compute the sample means, the standard deviations. The big new thing here is, since I'm comparing two different means of two different samples, I calculate my standard error in a new way. It's a great big square root of the first standard deviation squared over the first sample size plus the second standard deviation squared over the second sample size, square root of that whole thing. We then use it to compute our test statistic based on the difference between our two sample means. Degrees of freedom is the smaller sample size minus 1. And then similarly, we can use this to make a confidence interval where on the average difference between the two populations, where the margin of error is based on this new standard error.